In this video, we're going to be taking a look at a bunch of standing waves in three different types of tubes. We have one that's closed on both ends, one that's closed and then open, and then one that's open on both ends. Now, basic rules are this: if you have a closed end, then you're going to have a node at that end. And if you have an open end, you're going to have an antinode at that end. Now, what that means is a node is a null point or dead point in the wave where the waves are going to sort of cancel each other out. And an antinode is the part where it shows the maximum amount of displacement and energy. So just a quick summary of how that's happening. We have a wave that's entering the tube, reflecting off the closed end, bouncing back. And then although this is an opening end, because of the change of pressure, there's some of the wave that is reflected back in the tube. So there's basically waves going back and forth, interfering with each other, and then creating a specific standing wave pattern by constructive and destructive interference. So if you have the closed end like this one, and it's closed on both ends, and you try to make the least amount of waves possible in here, it would be closed on this end and then close it off on this end as well. And then this one is open on both ends. So it has to be open here and then open here. All of those would be considered the first harmonic or the fundamental frequency for each of those different types of tubes. Okay, so you can either call it the first harmonic or fundamental frequency. They're referring to the same thing. Now, a good rule of thumb is this, is that each little eyeball shape is equal to half a wavelength. Although that's not a very scientific way of looking at it, it works for all of our different tubes. So we have a single eyeball shape here, so that is exactly half a wavelength. For this one, we have half of a half, so it is a quarter of a wavelength. And then for this one, we have another quarter and a quarter, so a half total. So if we take a look at everything as a single eyeball shape is half a wavelength, it's going to hold up pretty nicely. Now for the closed tube, the one that's closed on both ends, goes to the second and third harmonic. This one also goes to the second and third harmonic. The one that's closed and then open only has odd harmonics, so it goes from the third to the fifth to the seventh and so on. Also, another term that you might hear is overtone. Overtone is basically how many harmonics it is above the fundamental frequency. So this row would be considered the first overtone. This one over here would be considered the second overtone, and so on. Now, as we draw the next overtone or harmonic up in the series, basically all you're doing is adding one more additional eyeball shape or half a wavelength. So let's go ahead and add those to each one of the next couple tubes and see what they look like. So as you can see, I add an additional half a wavelength in each of my tubes. That's how you rise up by the smallest increment. So if you actually know how many wavelengths are in the first one, you have to actually just keep on adding a half. But we'll go ahead and pretend like they're each separate little problems. So remember, each eyeball shape is half a wavelength, so we have a half and a half. So we have one full wavelength in here. This one we have 3 halves. This one we have 1 1/4, so 3 quarters. And this one we have half and half, so 1, and then this quarter right here, so 1 1/4. This one over here we have half in the middle, 2 quarters on the outside, so we have 1 total. And the last one we have 2 halves in the middle, so that's 1, and then a quarter on the outside, so that's 1 1/2 or 3 halves. All right, so we know how many wavelengths we have in each of the tubes. Now a common follow-up question is finding out how long each of these wavelengths are. So you would need a little bit more information for these. So let's say, for example, that this tube is 50 centimeters. That would mean that the length of the tube is 0.5 meters once we do a little bit of converting there. And for the tube that's closed on both ends, you would use the formula wavelength equals 2 times the length of the tube divided by n. N is the number of the harmonic. For this one, the wavelength equals 4 times the length of the tube divided by the n value. And then this one is actually the same as the first one, 2L over n. Now what you do there is fairly simple. You have 2 times the length of the tube. We said that's 0.5 divided by, and then we're going to do this one over here. So there's, this is the third harmonic. So 2 times a half is 1, divided by 3 is 1/3. So we have 1/3 of a meter for our first one. For our second one, let's go ahead and do the first harmonic, or the fundamental frequency, which would mean that it's 4 times the 0.5 meter tube divided by 1, and then 4 times a half is 2, divided by 1 is still 2. And lastly, let's go ahead, let's do a second harmonic one, because we haven't done a second harmonic one. And then that would be 2 times the length of the tube divided by the second harmonic. 2 over 2 is 1, times 1/2 is just 1/2. So we have three different formulas you can put into place, all of which are fairly easy to use. You just have to make sure you have the length of the tube in meters, and then you plug in the n value, which is the harmonic number. For the first and last one, it's pretty simple because it just goes 1, 2, 3, 4, and so on. For the middle one that's closed and open, it goes by odd numbers. So just make sure you go up from 1 to 3 to 5, and then so on. So as a good rule of thumb, if you know the fundamental frequency for each one of them, what it looks like, and how many wavelengths there are, if you go one up on each one of them, you just add one more little eyeball shape, which is half a wavelength, and then you can get to the second, third, fourth harmonic, and so on. So I hope that was helpful to you. Thank you very much for watching and listening.